To start this video, I'd like to do an example of using L'Hopital's rule, just to show you how it's done, and also to introduce some conventions and notations that come around with using L'Hopital's rule that mathematicians are very firm about, and that people who are just learning don't quite understand. So I'd like to try my best to explain the reasoning behind that rigidity and notation to hopefully bring us a little bit closer to the same page. So one thing before we even start with computations involving L'Hopital's rule that's very important is we have to check that the limit that we're considering is truly giving us an indeterminate form. If you try to use L'Hopital's rule when you do not have an indeterminate form, there's absolutely no guarantee that these two limits have the same value. That's not necessarily the case. And in fact, if these two values were to be equal, it would be very coincidental. So it's very important when using L'Hopital's rule that somewhere on your sheet of paper you've shown that you truly do have an indeterminate form so that you can use this powerful technique. Now, most people will buy into that, but when they go about checking that they have an indeterminate form, what they write is that this limit equals 0 over 0. And math teachers, in particularly those that grade AP Calculus exams, get very upset by this notation. This troubles them greatly. And on an AP exam, if this is written anywhere on your paper, I can guarantee you're losing points. What they want to see is that equal sign change to an arrow. And I would like to see that as well. Let me try to give you a little bit of a rationale as to why this makes mathematicians so sad. Remember that mathematically, we can't divide by 0. So when a mathematician writes 0 over 0, they are referencing an indeterminate form. It's like a concept, a thing that doesn't make any sense. This thing over here, in fact, the purpose of using L'Hopital's rule is to attempt to get a number for this. This 0 over 0 is really representing a small number divided by a small number, which could truly be anything. And so when we assert that anything in the world and a concept is equal to a specific number, then that feels wrong. The equal sign is very holy in mathematics. It means the thing over here has precisely the same numerical value as the thing over here. The thing over here is not a numerical value. And so to a mathematician, when you say a thing that is not a number is exactly equal to a thing that is a number, it makes them sour. However, if you say that this limit is approaching an indeterminate form, then that's something that they'll make you much happier. You haven't abused that equal sign. That will be enough to earn you points on the AP exam for checking that L'Hopital's rule applies. I also need to see indication that you're using L'Hopital's rule. Remember that I am surprised that these two functions have the same limit. And so I would like to see a reasoning as to where on earth this equal sign is coming from in order to know how you knew that the limit of this function was equal to the limit of this function. So for me, I need to see some indication on a sheet of paper that you're using L'Hopital's rule when you present me with that equality. As an example, I would just combine these two things very simply by saying, notice that this limit is approaching the indeterminate form 0 over 0. And then I write the original limit I've presented with over here. I write an equal sign. I write what it's equal to by L'Hopital's rule, which is the derivative of the numerator, 1, divided by the derivative of the denominator, 4 times the cosine of 4t, limit as we approach the same value. And I write that equal sign with just an L'H over it, so I see right there why these two limits are equal. Another thing you could do is just omit that altogether and write more words. Thus, by L'Hopital's rule, this limit equals that limit. And I would find that perfectly acceptable as well. If you have some other sort of abbreviation for L'Hopital's rule, and it's clear that that's what you're doing, that would be fine as well. But I need to see that this limit is in an indeterminate form and somehow know very explicitly that you're using L'Hopital's rule. The benefit of L'Hopital's rule is that this second limit that we've gotten is absolutely not an indeterminate form. The number 1 just stays exactly as it is, and the limit, as t approaches 0 of the denominator, is 4. So this limit doesn't require any fancy machinery in order to compute it. It has a value of 1/4, and L'Hopital's rule is giving us that 1/4 is precisely the value of this limit. Now the last thing I want to do in this video is talk for one moment about continuous functions. Continuous functions, in a very informal way, are ones that you can draw without having to lift your pencil. This is a very strange looking function, but I could draw it without ever lifting my pencil off the paper. This function, when I get down here, the only way to get up this high, drawing it on a sheet of paper, would be to lift my pencil. And so this point right here is a discontinuity of the function. A thing that I used on the previous page was I used continuity of the cosine function in order to find the limit of 4 times the cosine of 4t. That is, all I did is took the value of t equals 0, plugged it in to this function, computed 4 times the cosine of 0, and got 4. The only reason I'm getting away with that is because the cosine function is a continuous function. In other words, the value of the limit as x is approaching something for a continuous function is precisely equal to the value that the function takes on at that point. That would not be true of a discontinuous function. Right here at 2, the function is approaching 1, but the actual value of the function is 2. The only good news is that almost all of the functions we use in a calculus course, sine and cosine, exponentials, logarithms, polynomials, those functions are continuous functions. In fact, those are all differentiable functions, which is even stronger than continuous. And so I have that ability to just plug in the value, and whatever the value is, that's what the limit will be. Now our next video is going to start with another example. In fact, I've called it an exercise because it's for you to do. So I'm just going to end this collection of videos with showing you that example so that you can work it on your own, and then when you're done with it, you can start the next video for the explanation of it.